So can you all see the presentation?
Yes, we can see the presentation.
All right. So the title of my presentation is evaluating the effect of pavement type and fuel consumption excess using finite element modeling. This work was conducted by my former graduate student, Nurmar Dakal, and myself. So if we start with a little bit of background, so it's well known that truck traffic consume a large amount of fuel, and this is estimated at about 200 billion gallons of fuel annually. And this accounts for about $800 billion of consumption every year. So it's quite a bit of money being spent on the fuel consumption of truck. And obviously, truck consumption originates from many sources. It originates from the aerodynamic of the truck. It originates from as part of our work here. Part of the consumption comes from the rolling resistance between the tire and the pavement. And the rolling resistance accounts for about 32% of the total energy consumption. So it's a significant portion of the consumption. And there has been a focus in recent years on the effect of pavement type on fuel consumption. There's a message from the chat. I don't know if it's for me or not, but anyway, I would keep going. So pavement type can make a difference with respect to the rolling resistance. And this was one of the motivation of our study here. So as I said, the rolling resistance will require energy for the truck to move and to overcome this resistance, and this is known as energy dissipation. And until now, there was no studies that have looked at the effect of asphalt mixes on the rolling resistance, and also pavement characteristic and the effect of vehicle speed. So these are three main factors that will affect the rolling resistance. And there was, before this work was done, there was really not much available in the literature, especially with the impact of asphalt mixes. No study has looked into that. So what we did in our study is that we adopted a finite element approach to study the variation of the rolling resistance with pavement type, asphalt mixes, and vehicle speed. So the objective was to study the variation in energy dissipation and rolling resistance with the asphalt mix viscoelastic property, the pavement characteristic, and the vehicle speed. These are the three main factors that we evaluated in our work. And in order to achieve this objective, we developed a three-dimensional finite element model. We validated this model, and then we used this model to estimate the fuel consumption excess due to the pavement type and the pavement characteristics. So research approach was literature review. Then we did the finite element model. We validated the model. Then we obtained the results and we analyzed them. And these are the four main types. So start with a little bit of background. So you can analyze the pavement using three main approach. some of you probably already know about that. So the plane strain approach has been used for quite some time because it's relatively simple. It's shown here. So we neglect the third dimension in the analysis. And again, we assume that the load is represented by a line load. So we completely ignore the third dimension. And there has been work done in the past that have shown that this method is may not it can be accurate in some cases, but it may not account for example, the vehicle speed, and it may not account for example, the longitudinal strain when the load is moving. The second approach, which is an axisymmetric approach, is basically the middle ground. Is that even though we don't consider the third dimension, but we assume that we are dealing with a 3D structure that is symmetric throughout the rotation line in the middle. So we can only model one load, and it's assumed as a circular load. So again, it has some limitation because you cannot account for the variation in contact pressure and the variation in speed. So again, it has been shown to be mostly accurate, but it has limitation in its application. The third approach, which is the three-dimensional approach, it can account for pretty much everything that you have. So it can account for the speed, it can account for dynamic loading, it can account for the interaction between the layers. So it's a very powerful tool when it comes to pavement analysis. The main limitation is that it's a little more complicated, so it requires advanced computational tools, and it requires more computational powers in order to conduct and to run the model. So we use the three-dimensional method in this study because obviously we wanted to account for the vehicle speed and the accurate representation of the loading area. So we use abacus in our finite element model, and we use CAE, which is a relatively recent development in abacus because it doesn't require advanced knowledge of finite element model. So this process, we start by defining the part, then the material properties, then we assemble the part together, then we define the loading steps, the interaction between the layer, the loading magnitude, then we mesh the assembly, and then we execute the job, and then we visualize the results. So the part that we created, this is a relatively overview of the different parts. So this is for concrete pavement. In that case, we simulated the dowel bars and we simulated the joints. So you can see here we have the different part of the model. And as I said, after you create the different parts, you are able to mesh it, and you can see the overview of the general models that we created for concrete pavement. With respect to flexible pavement, so these are the dimension of the model, and we use viscoelastic constitutive models for the asphalt layer, and that's quite important because we wanted to look at the mixed properties, and this is the best way to do that. And for the underlying layer, we use elastic constitutive modeling based on the available data that we had for the study. We simulated the interaction between the layers using a friction model, and we also assigned a friction between the concrete and the dowel bars. So in order to simulate the load transfer between the rebar and the concrete material. For the flexible pavement, we simulated different structures. So we simulated a model that represents high volume traffic. We simulated another pavement structure that would be used for medium traffic, and a third to simulate low volume. And this is the structure that we simulated for concrete pavement. So these are kind of typical pavement designs that we would use here in the state. And again, it's meant to look at the variation of energy dissipation for the different pavement structures. We also simulated different mixes. So as I said, this is something that was not considered in the literature. So we wanted, for example, to see if you use a mix with high RAP, how will it affect your fuel consumption? So obviously, when you think about RAP, you think about saving in material, but no one has considered its effect on fuel consumption, and that's what we wanted to look at in the study. So we had 5 different asphalt mixes, as you can see here, and we incorporated these mixes in the surface layer that is shown here to consider their effect on fuel consumption. We also considered different vehicle speed, as I'm going to show you in the next few slides. So to simulate the process of load movement, we use an approach in Abacus known as quasi-static. So quasi-static is not a real dynamic, but it accounts for the time-dependent behavior of the material. So it considers the creep behavior and the time delay that you obtain with viscoelastic material. So it's simpler than dynamic analysis, and it also allows us to simulate the vehicle speed in the process. We also adjusted the boundary condition of the model in terms of displacement and rotation degree of freedom. So to simulate the vehicle speed, we use different increment time. So obviously, when you are traveling at higher speed, you spend less time loading the pavement. So we calculated the increment time that will correspond to the different vehicle speed, which we consider, which was 10 miles an hour, 30 miles an hour, 45 miles an hour, 60 miles an hour, and 75 miles per hour. So these are the 5 speeds that we considered in the analysis. With respect to the elements that we use, so we use a regular 3-dimensional 8-node brick element to simulate the different layers. And obviously, as it has been done for quite some time, we always try to use smaller elements in area where you have high stress variation. And in order to try to reduce a little bit the computational time, we use larger elements as we get deeper into the pavement. So with respect to the load, again, we simulated the loading area. So we simulated the dual tire assembly. And to simulate the movement of the load, we gradually shifted the loading area over the surface of the model. And this loading area is basically representing the footprint of the tire. So the footprint of the tire was obtained from a previous study. And these are the non-uniform tire contact pressure. So these were measured in a previous study. And we simulated exactly the same loading area into the finite element model. So again, this is something that provides higher accuracy because you don't consider a circular load. We consider exactly the same contact dimensions that we measure in the field. So to simulate the movement of the load, we use this shape that you see here. So this is the amplitude of the load. And basically what happens is that you apply your load in a part of the model, and then you keep the load constant for a small time. Then you reduce the load, and then you go to another contact area, and you start increasing your load. Then you keep it constant, and then you decrease. So again, this method has been developed during my PhD study. So it's almost 15 years ago, but it's a very smart approach in order to simulate the movement of the tire. And the time here is varied depending on the speed. So if you have higher speed, you reduce the loading time. And you can see here the process of applying the load. So keeps on increasing, and then it moves as it keeps on shifting. So it's a process that is very effective in simulating the movement of the tire. And again, if you think about it, this is the best approach, except if you are able to simulate the actual tire itself, which again, it's much more time extensive if you select the second method. So this video here show you the movement of the tire. So you can see here we simulate the movement of the loading as it passes through the pavement. So it's a time-dependent process. All right, so with respect to material property, as I said, we use a viscoelastic approach, which was based on the generalized Maxwell model. So this is the generalized Maxwell model, and it represents a number of Maxwell elements. You can see them here, and they are in parallel. So this model has been shown to be quite accurate for asphalt mixture, and we use it to simulate the material behavior of the hot mix asphalt. To fit the generalized Maxwell model, there is a built-in tool in Abacus that allows you to do that. So you enter your experimental data, and then it shifts and it determines these material parameters so that you have an accurate representation of the viscoelastic behavior of the material. With respect to model validation, so in my opinion, model validation is very important. If you want to make sure that your model is valid, you have to compare it with some type of experimental result. So we had some of the data obtained at the accelerated loading facility in Louisiana, and these data were obtained at a speed of 10 miles an hour, which was one of the speeds that we simulated in the model. And the measurements were obtained using instrumentation. So we had pressure cell and we had strain gauge, and these measurements were compared to the finite element model to see how accurate our prediction is. When we compared the measurements, we had quite a good comparison, and I'm going to show you this comparison here. I think I have them. Yes, it's coming in the next slide. So this is a comparison between measured and calculated vertical stress. So you can see we have a very good agreement here with only 5.6 error comparing the finite element model to the experimental measurement. You cannot compare stress only. You always have to compare stress and strain, or stress and deformation. So we compared the strain, the longitudinal strain here And you can see that longitudinal strain is quite interesting because it starts with compression, then it changed to tension, and then it changed to compression again. So we had also quite a good agreement between experimental measurement and model prediction. So after we validated the model, we started using it for the purpose of our study, which was energy dissipation calculation. So we energy dissipation is obtained for viscoelastic material using this equation, and it basically calculates the dissipated energy through the creep strain. So if you are familiar with the creep, so a creep is basically the loss uh, energy, and this loss energy is related to the energy dissipation. And we obtain the energy dissipation uh, for different conditions. So, for example, here we had dissipated energy for low volume design, medium design, high volume, and the rigid. So you notice here that there is quite a bit of difference between the rigid pavement and the flexible pavement. And the energy dissipation in the rigid pavement was less than what we calculated for flexible pavement. And we also looked at the energy dissipation with vehicle speed. So obviously, at lower speed, you have higher dissipation, as you can see here. So that's for flexible and that's for rigid. And as the vehicle speed increase, you have less energy dissipation happening inside your pavement. So again, this energy dissipation comes from the amount of deformation that the pavement is experiencing. And because rigid pavement is stiffer than asphalt pavement, the energy dissipation is less in rigid pavement than in flexible pavement. And we also looked at the energy dissipation with the type of asphalt mix. And we found that when you use RAP, you can see it here, we have less energy dissipation. So why is that? Because RAP is a much stiffer mix than the version mix, and that's why you get less energy dissipation when you use RAP than when you use version material. So we also calculated the fuel consumption as related to the dissipated energy. So this is the energy consumption that is related to the energy dissipation that we calculated. So obviously that you are going to see that there are much smaller values than the fuel consumption of the total truck, which accounts for all factors during movement. So the fuel consumption excess was lower for low volume pavement, and it was lower for rigid pavement because you have less energy dissipation. And it was higher in pavement with greater HMA thickness. And the results are showing here. So you can see this is the fuel consumption excess in a liter for 100 kilometer travel. So you can see, for example, the fuel consumption for a rigid pavement is less than for flexible pavement. But one thing I want to point out is that, in generally speaking, the fuel consumption that is related to the dissipated energy is a very small percentage of the total fuel consumption of the truck. So fuel consumption with vehicle speed, we didn't find a large variation for rigid pavement, but we found it to increase when the vehicle is driven at a very low speed. And it was lower. Uh, uh, I'll keep on going. I'm almost finished. So it was lower by about 85% at 10 miles per hour as compared to 75 miles per hour. So this is a variation of fuel consumption with the speed. So you see that the fuel consumption decreased with the increase in vehicle speed, and obviously it's higher for flexible than for rigid data. I think someone has his mic on, so try to mute yourself. All right. So with respect to the mix type, we found that the fuel consumption was lower for stiffer mix. So it was, for example, it was higher for 70 conventional as compared to 70 RAV40, which had 40% RAV. So you can see here the results. And obviously, this is an added benefit of using RAV. So one would think that RAV is reducing material consumption, but also it reduces fuel consumption. But generally speaking, as I said, the effect of the mix and pavement type as compared to the overall truck is not as big as you may think. So it's not a very big fact. We also did a cost analysis considering the price of the fuel. So the cost saving for rigid pavement is not that much. So it's $0.018 for every 100 kilometers. So it's a small cost saving. Also, if we use a stiffer mix, you will save that much as compared to using a version mix or a conventional mix. But as I pointed out, is that the cost, fuel cost associated with energy dissipation is a very small part of the total fuel cost. So that's the variation of the cost for the different mix. And again, the one with 40% RAP was the one that was associated with the lowest amount of cost as related to energy dissipation in the pit. So in conclusion, fuel consumption excess was found to change with the stiffness of the top layer, so whether you have flexible or rigid pavement, and the thickness and the speed, and the influence of energy dissipation, even though it's small, so it's a very small percentage of the total consumption of fuel. And for future work, we would like to consider or to simulate the entire tire moving on the pavement surface. And we would like to consider the surface roughness. So again, we assume that we have a smooth pavement. Obviously, when you have a rough pavement, the results will vary. So this is a factor that would be really important to consider. And also, if we consider new technologies such as wide base tire, that's also something that would be very interesting to look at. And we would like to consider the cost analysis considering the different part of the entire fuel consumption of the truck, not only the energy dissipation. So with that, I conclude my presentation. I would be happy to answer any questions that you may have.
Thank you very much, Dr. El-Sifi, for the excellent presentation. Please, we have 5 minutes if anyone has questions to Dr. El-Sifi.
Yeah, hi. I have a few questions. This is Kieran with the Tran-SET group, and we're actually performing a federal highway study where we're looking at several models, both structural response models as well as pavement surface characteristics models for fuel consumption. And it's a great study, Mustafa. I really liked your approach. One thing I was noticing, since especially when you're looking at flexible pavements, are you considering the effect of temperature? And then a second question there, I have several questions, I might call you actually, but the second question here is also, were you able to take your model and compare it with the MIT's deflection model or UIUC's Dr. El-Khadi data model and Karim Jati did a structural response model? So did you compare your results with any of their models?
All right. So with respect to the temperature, so that's a good question. Our model can easily be shifted to different temperature. For our study, we looked at 25 degrees C, but again, this is something that can be easily changed. And obviously, if you increase the temperature, you will have more energy dissipation. And if you decrease it, you will have less energy dissipation. So this is a factor that we did not consider, but it can be easily looked at from our study. With respect to the work that was done at MIT, it was not based on finite element model. I know that unfortunately, when this study came out, there was a lot of concern and question about its validity. And again, we did not compare it, but it's a completely different approach. Like our approach, I think, is more adapted to pavement engineering. If you allow me to say that we are, I am a civil engineering. I know how pavement work, and that really helped me in the analysis. And that's why that we have more confidence in our results as compared to other study in the literature.
Thank you very much, Dr. Zifi. Anyone? We have time for one last question. Okay.
Thank you very much for your nice presentation. I just want to say that I think your approach is more sound than what the MIT has done. The MIT has looked at the deflection under a flexible and a rigid pavement, and that small difference in deflection, they used to estimate the fuel consumption due to rolling resistance. And I think an important highlight of your work is the fact that this difference between the two pavements is very, very small. The fuel consumption due to this difference, either you look at deflection or the dissipated energy, really has a very, very small impact on the entire fuel consumption. The speed of the vehicle, the wind, the direction of the wind, the inflation pressure of the tire, all of these factors will affect significantly, I think, significantly more the fuel consumption than just the pavement type.
I absolutely agree with you, Stefan. And actually, you emphasize really what I want to point out from our study is that the pavement type, in my opinion, is a very minor factor as compared to the speed, the inflation of the tire, and actually the surface roughness. Surface roughness, if you are driving on a new road with an IRI of, let's say, 85, the fuel consumption would be much less than if you are driving on a secondary road with 280 inch per mile IRI. So there are other factors that relate to pavement, but these factors, in my opinion, are much more important than the pavement type. So we report our results, which shows that rigid obviously will have less energy dissipation, but overall, when you look at the whole picture, this is a very minor effect with respect to fuel consumption of trucks.
Yes.
Yeah, the
Thank
other
you
thing
very
you've
much.
done, Mustafa, there is that you've actually isolated the effect of deflection from roughness. So you've taken away that, the dynamic impact of that roughness that would cause in interacting with the deflection. So it's really a nice study. And a lot of people have done the roughness study, so you can kind of, put them together to see how much influence does deflection have and how much roughness has, and, sort of, in a way, put them together. Really great job. Thank you.
Thank you, Kiran.
Thank you very much, Dr. Zifi, for this excellent presentation. With this, we conclude today's session on pavements. Thank you very much for everyone who attended the meeting. Thank you.